Okay, we're taking a look at problem. It's a Serway problem. It's 24.61. It's a real pain. It's not a flat sheet. It doesn't have the same kind of circular or spherical or cylindrical or even a flat surface, but we're going to use a similar technique to it. Okay. And to do it, we have to actually use a similar, the same kind of logic we used when we did when we looked at just the sheet. We gave it like a minimal thickness. So let's say I'm going to draw it here. So here is the actual thickness of it. Okay, here's the sheet itself. Again, I'm just going to draw like not the whole thing, but just a little bit of it. Again, it's infinitely tall and infinitely thick, so I'm just drawing a little piece of it. Okay. So we need a Gaussian. So you can use any Gaussian. You can use a box. You can use. I'm a big fan again of this. I'm a big fan of just like a little can. Okay, and the can is going to be like just going out from the outside because we're doing the outside. It's going to be a can that goes into the thing. And it's going to go just a little bit in over here. So you can see it's just going to cut into the center of it. Okay, and the field from this is all going to go out from the sun. It's going to go out in this direction, like along the z-axis, okay? Because it's infinite in all those other directions. That's the E field. So it's not going to go through the sides of the can. It's only going to go through the lid of the can. So when we're looking at area, we're just going to look at the area of this piece over here. Okay, that's the only area we're going to look at. So we don't even need that thing anymore. I just wanted to emphasize that. Come on. Okay, cool. So, all right. So first, like any good Gauss's law problem, we're going to look at Quank. Okay, and Quank is just going to be, because it's just a big slab of stuff, and doesn't have a constant density. Even if it had a constant density, we'd really just be finding, if it was constant density, we'd just take the density times the volume. Since it doesn't, we're going to have to take the density times the volume, times the integral of the density times the volume. So it's going to be, so Quank is going to be rho dV. Okay, and again, we chose the can as the section. And again, the part that's going to be in there is this little section of the can that's on the inside. I don't know if you can see it, but it's that little section of the can that's on the inside. And that little section of the can is going to be, it's going to be just however much of it we're going to get. Okay, and again, we're going to have to add that up through the whole can. So for us, it's going to be rho pi r squared dx. Remember, x is the one we're looking at. And we're going to go from 0 to d over 2. We're just going to take 1/2 of it. They want us to look at just like each separate region of it. Okay, like when it's going one way, it's going to have a field that goes to the right. When it's on the right hand side, the other way it's going to have a field that goes to the left, and we're going to do that as well. Okay, so we're just going to put that in there. Okay, so that's going to be the area there of our little, and then we're going to take down the volume. So, okay, so, and we have an expression for it, which we've got to sub in now. So that's going to be, I'm going to pull the constants out. I don't know what r is, so that's a constant. Okay, and it's going to be c x cubed dx from 0 to d over 2. Okay, well, that's not a hard thing to integrate. It's just x to the 4th over 4. So I'm going to bring it over here. So so it's c pi r squared. And it's going to be x to the 4th over 4. Oh, I'm sorry, it's squared, isn't it? So it's x to the cubed over 3. Sorry. Okay. And then that's going to be from, that's going to be between 0 and d over 2. Okay. Okay. When you sub that all in, you get pi c r squared. What is it? It's a d cubed over 24. Okay, so that's what quank is. Okay. All right. Next, we have to actually go back and do the. Next, we have to actually do the. Find out what the electric field is. We'll do that by finding Gauss by using Gauss's law. So E dot dA equals quank or epsilon naught. We just derived the expression for this. It's going to be pi, and pardon me, I'm going to rearrange this slightly from how I wrote it before. Pi r squared c d squared over 24 epsilon naught. Okay, and this is going to be E. Okay, and again, it's going to be constant because it's going to run constant through our little cap, and it's going to be pi r squared because that's the only area that it's running through. Go back to our little picture, and you can see it just runs through that area. Well, that turns out great because this divides out, and E is just going to be that. It's going to be cubed over 24 epsilon naught. Okay, so that turns out great. Okay. Now that's for the region on this side. Okay, oh sorry, that was not a very neat drawing, but on the right hand side, the field that goes like this. Okay. On the opposite side, it's just going to go the opposite way. So the field is going to go when x is greater than d over 2, or sorry, I write that correctly, is less than negative d over 2. Okay, this is going to be the opposite. It's going to be the same value. It's going to be negative c d cubed over 24 epsilon naught. Okay, and you can satisfy yourself by deriving it with the different limits if you want to do that. Okay, so we're looking at the part B where we're looking at the interior region. So it's this region that we're talking about here. Okay, so in order to do that, we're going to have to actually have a Gaussian that looks like that. Okay, and we're going to have, if this is or a Gaussian looks like a little, from the side it's going to look like a little square, but it's going to run the left edge. I didn't draw as neatly as I could. It should run right up against that x equals 0 line, that xy line that's drawn in the picture. It's still going to look like a can though. It's still going to have that shape where it's going to be a circle. Okay, like if you looked at it from the side, like where the YZ plane was, it would look like a can. Okay, so just like in the other one that we drew. Okay, so we've got to find quank first. Okay, and quank is going to be the thing that we've done a whole bunch. It's going to be the same integral basically. Okay. It's going to be still cx squared, but our limits are going to be from 0 to x because we don't have to grab everything that's on that side of the container. It's still going to be pi r squared, and it's still going to be dx because that's going to be the thickness of our container for each layer that we grab as we go from 0 to x. Okay, and we're going to get the same kind of thing. We're going to get cx cubed over 3, okay, and it's going to be times pi r squared. It's going to work the same way. We're still going to go back to Gauss's law. So E dot dA equals quank over epsilon naught. Okay, and it's going to be E. Again, remember, it's the same can, so it's going to be pi r squared. Okay, it's going to be the area because that's going to be the only part that the field goes through. Okay, and we're going to set that all equal to this whole thing over here, cx cubed over 3 times pi r squared. And again, the areas are going to divide out, and we're going to get the field is cx cubed over 3. Okay. I want to point out that's the positive side. That's when x is greater than 0. Okay. If you set the limits the opposite way, you get the exact same thing for the other side. If x is less than 0, then you'll get that e is negative cx cubed over 3. Okay. And that's all you're going to get for that. So that should be the way to do it.